We are now going to determine the equilibrium constant given a reaction in which one of the reactants or products, we are given its equilibrium constant at chemical equilibrium. So let's go ahead and kind of let's look at our particular problem here. And so what we have here is we have 0.5 molar of nitrosyl chloride is placed in a 1 liter reaction flask and heated to 227, and the system it reaches equilibrium. The contents of the reactor were analyzed and found at chemical equilibrium we have 0.028 molar of chloride. We're asked to calculate the equilibrium constant at this temperature. So what we have is we are given the initial concentration of nitrosyl chloride, and then we're given the concentration of the chloride at chemical equilibrium. And we're asked to solve for the Kc, the equilibrium constant. So let's go ahead and the method that we're going to use to calculate this, to determine this, is through the utilization of an ice diagram. So what we do is write down our reaction, and the nitrosyl chloride decomposes to nitrogen monoxide and diatomic chlorine. And what we'd like to identify is the equilibrium constant associated to the process once it's at chemical equilibrium. The way we're going to go ahead and determine this is through what is known as an ice diagram. And so an ice diagram is ICE. And those acronyms, the I stands for initial, C stands for change, and the E stands for at equilibrium. And from this, we are going to go ahead and determine the equilibrium constant. So we're going to go ahead and build this table. I am titling it in molarity. And let's fill in the information that we are given in our problem. All right. So what we're given here is we have the initial concentration of nitrosyl chloride, and that was given to us at 0.5 molar. And then we're given the equilibrium concentration of the chloride, the diatomic chloride, once it's achieved, the reaction has equilibrated. And that value was 0.028. So from these two values, we're going to determine the equilibrium constant. Now the equilibrium constant, based on the law of mass action, equals the concentration of NO squared multiplied by looking at the balanced chemical reaction, diatomic chlorine products divided by the reactants, and the nitrosyl chloride, and that squared. So what we want to do here effectively is we want to calculate all the values at chemical equilibrium and place them into our equilibrium constant expression. All right, so how we're going to go about doing this, let's just go ahead and we're going to go ahead and, based on the top row, the fact that we are not given, let's complete our top row, which is initial. The fact that we are not given any concentrations of the products at equilibrium, the products initially, we are to assume that those values are 0. The bottom is at chemical equilibrium, and for the chlorine, because we are given its equilibrium concentration, the change is from its initial state to its equilibrium value, and therefore it has gone from 0 to a 0.028. The change in molarity is it has increased from the 0 to 0.028, and that'd be a positive sign. So the bottom row is essentially the tally of the top two rows. So that gives us the change of Cl2. What we'd like to identify is the change associated to the nitrogen monoxide. And so what we can say here is, based on the balanced chemical reaction, we have the concentration of the NO equals twice the concentration of the Cl2 based on the balanced chemical sentence. So therefore, what is the change in concentration of NO? It'll equal 2 times the 0.028. And so its change in concentration equals a 0.056, and that would be molar. So we're going to come back now and place in the change of NO, and it has gone from 0 and increased by a 0.056. And then at chemical equilibrium, if we tally the two rows, it'll equal 0.056. Those are the products. All the products are generated from the reactant. And so we'd say that the reactant in approaching chemical equilibrium has decreased. By what value? Well, if we look at the stoichiometric ratio between nitrosyl chloride and NO, it's a 2:2 or 1:1 ratio, so it will decrease by 0.056. And then at chemical equilibrium, how much of the nitrosyl chloride will we have? We will have 0.444. We have completed this bottom row, and all based on that, we can plug it into our equilibrium constant expression and determine the equilibrium constant. So let's go ahead and plug in those values. And so we will have Kc equals NO 0.056 squared multiplied by 0.028 divided by the nitrosyl chloride, which is equals the 0.444 squared. Kc equals, let's go ahead and do stepwise, the square of 0.056 equals 0.00314 multiplied by 0.028, value hasn't changed, divided by 0.444 squared, which is 0.197. Kc equals, we go ahead and calculate that, equals 4.5 times 10 to the minus 4. We have solved for the equilibrium constant given the initial concentration of a reactant, the equilibrium concentration of one of the products, and once again, this equilibrium constant is unitless at 4.5 times 10 to the minus 4.